Today we will have lesson 6, row space, column space, and null space. We will study some important vector spaces that are associated with matrices. In this lesson, it will provide us with a deeper understanding of the relationships between the solutions of a linear system and properties of its coefficient matrix. So we have here, we need to recall that vectors can be written in comma delimited from or in matrix form as either row vectors or column vectors. The first definition will show us an m by n matrix wherein you could see the row vectors, which denoted by r sub 1, r sub 2, and 2r sub m, and the column space or column vectors of A, which denoted by c sub 1, c sub 2 to c sub n. Example number 1, row and column vectors of a 2 by 3 matrix. Let matrix A is equal to the set of 2, 1, 0, 3, negative 1, 4. The row vectors of A are r sub 1 is equal to the set 2, 1, 0, and r sub 2 is equal to the set 3, negative 1, 4. And the column vectors of A are c sub 1, c sub 2, and c sub 3, wherein c sub 1 is equal to 2, 3, c sub 2 is equal to 1, negative 1, and c sub 3 is equal to 0, 4. We have here another definition, which is definition number 2, that states that if A is an m by n matrix, then the subspace of Rn spanned by the row vectors of A is denoted by row A and is called the row space of A, and the subspace of Rm spanned by the column vectors of A is denoted by col A or called the column space of A. The solution space of the homogeneous system of equations Ax is equal to 0, in which it is a subspace of Rn, and it is denoted by null of A, or called the null space of A. We will use this definition in the following discussions. However, you need to consider these two general questions along the way. Question number 1. What relationships exist among the solutions of linear system Ax is equal to B and the row space, column space, and null space of the coefficient matrix A? Question number 2. What relationships exist among the row space, column space, and null space of a matrix A? Starting with the first question, suppose that matrix A and x is equal to x sub 1, x sub 2 to x sub n, which is it follows from the section a while ago, or the equation a while ago, that if c sub 1, c sub 2, c sub n denote the column vectors of A, then the product of Ax can be expressed as a linear combination of these vectors with coefficients from x. That is, Ax is equal to x sub 1, c sub 1, plus x sub 2, c sub 2, plus 2x sub n, c sub n. Thus, a linear system Ax is equal to B of m equations in n unknowns can be written as x sub 1 c sub 1 plus x sub 2 c sub 2 to x sub n c sub n, which is equal to b. From which we conclude that ax is equal to b is consistent if and only if b is expressible as a linear combination of the column vectors of A. This yields the following theorem, which is theorem 4.8.1. A system of linear equations ax is equal to b is consistent if and only if b is in the column space of A. So for example, a vector b in the column space of A, in which we will let ax is equal to b be the linear system of the following, in which matrix A is equal to negative 1, 3, 2, 1, 2, negative 3, 2, 1, negative 2, in which we have here the coefficients x sub 1, x sub 2, x sub 3, which is equal to the constant of the linear equations 1, negative 9, negative 3. Show that B is in the column space of A by expressing it as a linear combination of the vectors of A. So we have there the values of B, which is 1, negative 9, 3. So if you will show this, you need to use the Gaussian elimination, in which you could also try to verify, wherein you could arrive with the following solutions. We have x sub 1 is equal to 2, x sub 2 is equal to negative 1, x sub 3 is equal to 3. It follows from this and equation 2 that 2 times the first column minus 1 of the second times multiplied to the second column plus 3 multiplied to the third column, which is equal to b. So the relationship of ax is equal to 0 and ax is equal to b, we will explore this between the solutions of homogeneous linear system, wherein ax is equal to 0, and the solutions of the non-homogeneous linear system, ax is equal to b, with the same coefficient matrix. These are called corresponding linear systems. By the way, or by way of example, we will consider the following linear systems that we will discuss in this in examples 5 and 6, and then again in example 3. So we have here the following matrices, wherein you could say the representations of the homogeneous linear system and the non-homogeneous linear system. You could see that this is A, and this is X, and this is equal to 0, wherein you could see here in the formula or in the equation of the solutions of a homogeneous linear system, wherein ax is equal to 0. And for the non-homogeneous linear system, wherein we have their matrix A, and we have x, which is equal to b. So ax is equal to b, which is a non-homogeneous linear system. Next, so we found the general solutions of these systems also to be, we have here in homogeneous, x sub 1 is equal to this, is equal to negative 3r minus 4s minus 2t. X sub 2 is equal to r. X sub 3 is equal to negative 2s. X sub 4 is equal to s. X sub 5 is equal to t. x sub 0 is equal x sub x 6 is equal to 0. And the non-homogeneous system, we have x sub 1 negative 3r minus 4s minus 2t. So you could see here, this is the representation of the homogeneous system, and for the non-homogeneous system we have this representation in column vector form. This is called column vector form. By splitting the entries on the right part and collecting terms with like parameters, we can rewrite these general solutions as we have here x is equal to r times the value there of c1. This is c1 actually. Yeah, this is c1, c2, and c3. We have rc1, rc2, and sc2 plus tc3, wherein this is a homogeneous case. The same with the non-homogeneous. However, the difference is that in the non-homogeneous system, there is a non-zero value of b, while in the homogeneous system, the value of b is 0. All are zeros. So in example 3 of the previous discussion, we observe that the three vectors on the right side are linearly independent and therefore form a basis for the solution space of the homogeneous system. Thus, it is illustrated in the figure below. In this equation 5, the general solution x of the non-homogeneous system can be divided into two parts: a basis x sub h. As you could see, this is the basis. Actually, how many bases we have? 1, 2, 3. So in this case, you have 3 bases. For the null space of the homogeneous system, and the term x sub 0, that is a solution of the non-homogeneous system. So we have here only one solution for the non-homogeneous system. In this case, the solution resulting from setting the parameters to 0. So this example illustrates the following general theorem, the theorem 4.8.2, wherein if x sub 0 is any solution of a consistent linear system, ax is equal to b, and if s is equal to the set of vectors v sub 1, v sub 2 to v sub k, is a basis for the null space of A, then every solution of ax is equal to b can be expressed in the form x is equal to x sub 0 plus c sub 1 v sub 1 plus c sub 2 v sub 2 plus 2c sub k v sub k. Conversely, for all choices of scalars c sub 1, c sub 2, c sub k, the vector x in this formula is a solution of ax is equal to b. Next, we have here another discussion of the basis of row space, column space, and null space. So in this particular section, we will focus on the second problem posed earlier a while ago, and finding the relationships between the row space, column space, and null space of a matrix. We begin with the following theorem. Theorem 4.8.3 states that row equivalent matrices have the same row space. Means they have the same. Row equivalent matrices have the same null space. So if you have a row equivalent matrices, both of them it has both the same row space and null space. And theorem 4.8.4 also states that if a matrix R is in the row echelon form, then the row vectors with the leading ones, which is the non-zero row vectors, form a basis for the row space of R, and the column vectors with the leading ones of the row vectors form a basis for the column space of R. So we will have such an example of this. So for example number 3, in which it relates to the theorem 4.8.4, which is the basis for the row and column space of a matrix in a row echelon form, R or REF. So we will find the basis for the row and column space of the matrix. As you can see here, we have here already a given matrix in an REF form. Since the matrix R is in REF, it follows the theorem 4.8.4 that the vectors R sub 1, R sub 2, and R sub 3 have the same row equivalent and also have the same null space. It forms a basis for the row space of R and the vectors C sub 1, C sub 2, C sub 4, in which it forms a basis for the column space of R, as you could see here. Yeah. So this particular column forms a basis for column space for this matrix R, wherein you could see here, because I think this is because of the leading ones. Yeah, if you will look closely to the matrices. Next, example number 4, basis for a row space by row reduction. Find a basis for the row space of the matrix. Actually, this is a 6 by 4 matrix, wherein you could see an elementary row space. If you will you will use the Gaussian elimination to come up with a row echelon form of matrix A. So you have already the answer here. As you can see, there are leading ones. Leading ones here. Column 1, column 2, and column 5. So you could really identify easily the number of bases based on the leading ones that you could see in a row echelon form. However, you could also transform it first into this particular form, R sub 1, R sub 2, and R sub 3. So, how many bases do we have here? 3. Column 1, column 3, and column 5. There are 3 bases. So, in bases formed from row and column vectors of a matrix. If a matrix A is reduced to a row or REF, we know how to find a basis for the row space and column space of R. So moreover, we also know that the basis obtained for the row space of R is a basis for the row space of A. What is not true, however, is that the basis obtained by the column space of R is also a basis for the column space of A. So the problem being the elementary row operations can change the column spaces. However, The good news is that the elementary row operations do not change dependency relationships between column vectors. To make this more precise, suppose that W sub 1, W sub 2, W sub k are linearly dependent column vectors of A. So there are scalars that are not all 0, for which C sub 1 times W sub 1 plus C sub 2 times W sub 2 to C sub k times W sub k, which is equal to 0. So if we perform an elementary row operation on A, then these vectors will be changed into column vectors. At first glance, it would seem possible that the transform vectors might be linearly independent. However, this is not so, since it can be proved that these column vectors are linearly dependent and in fact related by an equation that has exactly the same coefficients in the previous equation. It can also be proved that elementary row operations do not alter the linear independence of a set of column vectors. All of these results are summarized in the following theorem, which is theorem 4.8.5, which states that if A and B are row equivalent matrices, then a given set of column vectors of A is linearly independent if and only if the corresponding column vectors of B are linearly independent. So in B, a given set of vectors of A forms a basis for the column space of A if and only if the corresponding vectors of B form a basis for the column space of of B also. So it follows that theorem 4.8.5b, that even though an elementary row operation can change the column space, it does not change the dimension of the column space. So we have here an example for this theorem. Basis from the columns of A. Find a basis for the column space of the matrix. Matrix A, wherein we have here we have here a 6 by 4 matrix that consists of a column vectors of A. We observe in this particular example, wherein you could transform it to the REF or the row echelon form, since you could see there that the first, third, and fifth columns contain the leading ones of the row vectors and the vectors. So it forms a basis for the column space of R. So there are 3 bases. Thus, the corresponding column vectors of A, which are these vectors, it forms a basis for the column space of A. For example 6, example basis for the rows of A. Find a basis for the row space of A, in which we have here the following given matrix of A, consisting of row vectors from A. Solution: we will transpose A, thereby converting the row space of A into the column space of, transposing it, AT. Then we will use the method of example 5 to find a basis for the column space of AT, and then we will transpose again to convert the column vectors back to the row vectors. So if you would transpose it, it yields to this following matrix, and reduce it to row echelon form. We could see here and obtain here the REF. So in this particular REF of the matrix, you could see the leading ones here in column 1, column 2, and column 4. Yeah, this one. And you transpose it again, you could yield a basis vectors, which is the row space of A. Example number 7. Basis for the space span by a set of vectors. So you could see here the following vectors span a subspace of R4 and find a subset of these vectors that forms a basis of this subspace. So V sub 1 we have here, V sub 2, V sub 3, V sub 4, and V sub 5, and V sub 6. So if we rewrite these vectors in column form and construct the matrix that has those vectors as its successive columns, then we obtain matrix A. For example, if you could verify it, you could see here the span of the set V sub 1 to V sub 6 is equal to column A. Proceeding as in this example, we see that the vectors V sub 1, V sub 3, and V sub 5 form a basis for span V sub 1 to V sub 6. How will you get this? Yeah, you could use the same process in the previous example on how to find the basis, the reason why these three vectors are the one that forms the basis. So problem, given a set of vectors, here we have another example where a set of vectors in Rn, find a subset of these vectors that forms a basis. Take note of the term find a subset of vectors that forms a basis for span S, and express each vector that is not in that basis as a linear combination of the basis vectors. So example 8, the basis and linear combinations. So in this particular example, we have here following vectors or 5 vector set that forms a basis for the subspace of R4 spanned by these vectors. Next, express each not of each vector not in the basis as a linear combination of the basis vectors. So you have already basis vectors there. So we begin by constructing a matrix that has V sub 1, V sub 2 as it column vectors, as a column vectors. Yeah. So then after showing it, the first part of our problem, we reduce the matrix to REF or RREF, which is reduce it to REF and denoting the column vectors by the resulting matrix. As you can see, we could easily identify the basis by looking at the leading ones. So in this case, you could see that the leading ones are W sub 1, W sub 2, and W sub 4. These are the basis for the column space of this particular equations. And we have here the basis of the column space. And for solution B, we will start by expressing W sub 3 and W sub 5 as a linear combination. So this particular column space, wherein you could make it as a linear combination, and the simplest way of doing this is to express W sub 3 and W sub 5 in terms of basis vectors with numerically smaller subscripts. Accordingly, we will express W sub 3 as a linear combination of W sub 1 and W sub 2, and we will express W sub 5 as a linear combination of the vectors w sub 1, w sub 2, and plus w sub 4. By inspection, we have these linear combinations are w sub 3 is equal to 2 w sub 1 minus w sub 2, and w sub 5 is equal to w sub 1 plus w sub 2 plus w sub 4. Yeah, okay, we call this as the dependency equations. The corresponding relationships are v sub 3 and v sub 5. Lastly, in this lesson, you need to take note of the basis for the space spanned by a set of vectors. So there are 6 steps that you need to consider. Step 1. Form the matrix A, whose columns are the vectors in the set S, which is equal to v sub 1, v sub 2 to v sub k. And for step 2, reduce the matrix A to reduced row echelon form R. Denote in step 3, you denote the column vectors of R by w sub 1, w sub 2 to w sub k. Step 4, identify the columns of R that contain the leading ones. The corresponding column vectors of A form a basis for span S. This completes the first part of the problem. And for step 5, obtain a set of dependency equations for the column vectors w sub 1, w sub 2 to w sub k of R by successively expressing each w sub I that does not contain a leading one of R as a linear combination of the predecessors that do. And in step 6, in each dependency equation obtained in step 5, replace the vector w sub I by the vector v sub I for I which is equal to 1, 2 to k. And this completes the second part of the problem. And that's all for lesson 6 in row space, column space, and null space. Thank you very much for listening.